my name is Sasha, and in the following I'll present a paper that was written together with my colleagues Yasmin, Alex, George, and supervisor Ode with the title Self-Supervised Log Parsing. Current IT systems are a combination of complex multi-layered software and hardware, and today billions of devices and users depend on the availability of these large distributed systems. They enable applications of ever-increasing complexity and system diversity, where many technologies such as the IoT, databases, operating systems are used. The complexity and diversity of these systems relate to high managing and maintenance overhead for the operators to a point where they are no longer sufficient to holistically operate and manage these systems. Therefore, service providers are deploying various measures by introducing additional AI solutions for the anomaly detection, error analysis, and recovery to the IT ecosystems. Of course, the foundation for these data-driven troubleshooting solutions is the availability of data that describe the system state. So, software developers often record critical system information and system status into a log file for the purposes of analysis and troubleshooting. Practically, logs are available in every computer system, and they are a valuable data resource for understanding system behavior. The first step for understanding log information and their utilization for further automated analysis is to parse them. Manual log analysis and log parsing is becoming infeasible, so automation is the key for detecting any problems. The question raised is basically how to improve over the current state of the art in this paper. Just to give you a broad overview of what parsing is, if we have a look at the first log message, so we have total of 77 errors, DDR errors detected and corrected. So the 77 is the variable part, and the template part is total of DDR errors detected and corrected, which is the parsing task. We want a method that parses the logs close to a human operator, and we have it on the right hand side. So the method is based on a model that is a self-supervised learning model which utilizes transformer architecture. Self-supervised learning is a form of unsupervised learning where parts of data provide supervision. To build such model, the learning task is formulated such that the presence of a word on a particular position in the log message is conditioned on its context. The key idea for the parsing is that the correct prediction of the masked word means that the word is part of the log template, and incorrect is a parameter or a variable. The advantages of this approach are that it can produce both a log template and a numerical vector representation, while domain knowledge is not needed, and that log templates are state of the art at this moment. With this, we conclude the overview of the method. To give a broader overview and motivation for such model, we first identify the limitations in the previous parsing methods. All parsing methods, starting from the simple regular expression to method using parsing trees, are specialized in parsing certain log types, and thus they limit the performance scores and generalization of these methods and models. So additionally, large systems consist of diverse software and hardware components that render intricate to maintain this manual effort. Additionally, frequent software updates necessitate constant checking and adjusting of these statements, which is a tedious and error-prone task. The main reason is, as I mentioned, using log-specific heuristics or data-dependent manual rule extraction methods, and if the data changes, they cannot simply generalize or do well. Different from the current state-of-the-art heuristic-based methods, our method does not require any domain knowledge because it's based on language modeling. Here we consider three log messages as examples and further motivation. So we have state up reported for the network interface, state down reported for the network interface. Interface needs reconfiguration when down. So in regular expression methods, one could, for example, define up and down as variables, but then the third log message will be wrongly parsed because the third log message does not contain any variables and In the regular expression, down we recognize as variable probably. Otherwise, 1 and 2 would be wrongly parsed. Parsing trees methods based on parsing trees, for example, drain, which is the previous state of the art, would create here two templates for the first two messages, state up reported and state down reported, mainly because it uses a heuristic that it says that the variable parts appear in the last words of the template, not in the first one. And here the variable part is of course up and down. As a human, we would create two templates out of these three log messages. The first one would be state and then variable reported and so on. And interface needs reconfiguration when down. So this would be a full template. The main question that we need to answer is how do we know which are the templates as humans? So we believe that when we look at the larger context or the context of the log message, in this case we use the mask word predictions, and language modeling has larger potential than these heuristic based methods. Okay, so in this figure we depict the model architecture. To the input from the far left side, we provide the mask logs. First, they are passed through the positional encoding block of the encoder. The positional encoding block enables preserving the positions of the tokens in the logs via adding periodic functions to the vector representation of the tokens in the logs. Such modified inputs are further fed into the multi-head attention block. The multi-head attention block is a neural network architecture that implements the self-attention mechanism. It works via projecting of the input context for the mask token into various subspaces and aggregates them. Each projection is controlled by one of the heads of the multi-head attention. The multi-head block separates the input into three vectors: key, query, and value. It uses the key and the query of the current input representation to assign scores for the context tokens from the log to the current mask token. Having the parameters of the neural network as learnable parameters, it results in learning how the tokens forming the context of the current mask token influence the prediction of the mask token. The next layer of the self-attention mechanism consists of two feed-forward layers. They provide a richer representation of the underlying output from the multi-head attention mechanism. The layer normalization and the residual connection are used as standard techniques for improving the performance of the neural network. Output from the self-attention layer are fed through one layer network with softmax at the end that serves as a decoder. The softmax is used as a function to generate probabilities over the whole dictionary of words for basically how likely is the current mask token to be associated with each of them, conditioned on the context. The key inside that is, since the templates are the constant part of the log message, the network learns to promote higher probability scores for the mask tokens appearing on relevant positions, while discouraging the higher probability estimates for the parameter values. This allows application of simple thresholding on the prediction to generate the templates. Acquisition of the top ranked embedding token from the multi-head attention results in generation of vector embedding for the given log message that can further be utilized for downstream tasks, for example, anomaly detection. So basically we have a parsing, so the parsing task, and then moreover we achieve representational learning of the log messages, which is important for downstream tasks, as I mentioned. For the experimental setup of this whole method, we did exhaustive evaluation on a set of 10 benchmark datasets and 12 parsing methods, which are widely available and used for every new parsing method for evaluation. The evaluation metrics are parsing accuracy and edit distance, and We utilize log vector representations and evaluate their usefulness in supervised and unsupervised anomaly detection as downstream tasks. To illustrate one thing which is really important is that the previous methods only consider the parsing accuracy as the metric, but we found that it has a small drawback, and I will try to explain in the right side. So imagine we have the three same log messages as we had before, and there are possible templates. So first we can name them as A, and B. So just with the simple letters, and we can say that we parse them. And the parsing accuracy as is used in the literature of log parsing would say that we have 100% accuracy. But furthermore, in order to be compatible with previous research, but also to be fair enough that we have really human-like parsing, we included the edit distance metric that will compare the ground truth string and the predicted string. Okay, so for the results, as I said, we compared against 12 methods on 10 different data sets, and these are the summarization results. When we see that here is the new, on the right side is the NuLog, which achieves the highest parsing accuracy among all the methods. The log which is near the NuLog, which is BOA, it's best of all. That's a selection of the best of the previous methods achieved on particular dataset. However, closer to NuLog is the drain method, as I said, which uses parsing trees and heuristics for parsing. For the edit distance, here is the opposite, the lower the better. And again, we have the NuLog on the right side, and we have the best, which is again the best of all methods, and drain is again the closest to our method. So here you can see that the NuLog method also achieves the best edit distance. As a case study, we illustrate the application of the presented method for anomaly detection. To this end, we discuss two approaches, unsupervised and supervised approach. On the left side is given the application for anomaly detection in the unsupervised scenario, and here for each token of the log message is masked and then predicted. All respectively masked tokens that are in top predictions are marked as true predictions. We compute the percentage of the true predictions within the log message to decide whether the log message is anomalous. On the right side is given the application for supervised anomaly detection. We utilize the log message embeddings as a feature for supervised anomaly detection. First, the model is trained on the self-supervised masked language modeling task. Second, we replace the last softmax layer from NuLog by a linear layer, and it is fed with the vector embeddings of the log as produced by the multi-head attention. In such a way, we provide a fine-tuning of the weights of the network, and we have a classifier as anomaly detector. The results are given in the table. So we can see that for particular for the data set that we have, we achieve really good results. But additionally, we tested in several other data sets after the publishing of the paper, and we can safely state that it achieves fair enough results. It can be improved, so we have another upgrade of this paper especially for anomaly detection, not for parsing, where we utilize the same structure with slightly modified objective in order to perform better anomaly detection. We addressed the log parsing problem with deep language modeling. The method produces a numerical representation of the context of the log messages, which allows utilization in downstream tasks such as anomaly detection. We conducted experiments on 10 real-world datasets for parsing and evaluated against 12 log parsers, outperforming the existing approaches in most datasets. And our approach shows that log parsing can be performed with deep language modeling indeed. As final remarks, we believe that future research in log parsing and anomaly detection should focus more into generalization across diverse systems, transfer learning, and so on, where learning of meaningful log representations could further improve the troubleshooting task critical for operations of IT systems. Thank you for your attention.